going to cover four major areas of VRay: the light cache, quasi-Monte Carlo GI, color mapping, and environment lighting. The light cache and QMC GI render engines will take up the vast majority of this discussion, primarily because the controls and concepts for color mapping and environment lighting are smaller in scope and much easier to grasp. In Module 1, we only focused on one rendering solution, the irradiance map, and in this module we look at the last two that will be presented in this series of instruction. They are both very complex topics and can be very difficult to understand, but just like the irradiance map, when broken down they're really not so difficult to understand and can be understood quite painlessly. When I was deciding what topics to present for part 2 of these critical settings, I realized that color mapping and environment lighting needed to be included along with the various rendering solutions, not only because of the critical role they play in the typical visualization, but also because of their global impact. Although other areas of VRay such as materials, displacement, depth of field, etc. are obviously very important in much of our work, none of these has as much an immediate impact or direct impact on the actual lighting of our scene, and none need to be discussed so early on as these two concepts. Hopefully by the end of this module you'll have a good understanding on all these important concepts, and hopefully you'll have a good foundation with which to efficiently and effectively cover the remaining modules. So we'll start this module with an in-depth look at the light cache. Okay, so what is a light cache? Well, it's simply another set of complex algorithms used to approximate indirect illumination. Unlike some of the other GI solution types, the light cache has only been around a few years, and it was first developed by the makers of VRay. It's a fantastic lighting solution, and it's arguably the most widely preferred secondary bounce engine among VRay users. And there's two main reasons for this. One, it provides a great mixture of speed and quality, and two, it's very simple to use relative to other solution types. One of the things that makes it so easy to use is that it does not have a multitude of variables that control adaptive behavior like the irradiance map, and this alone makes it a much simpler solution to use. Nonetheless, it is still a complex creation that contains enough variables to confuse and overwhelm many users. In just a moment we'll jump right into some visual demonstrations that will make understanding this solution quite simple, but I want to talk for just a moment about some of the advantages and disadvantages of the light cache in comparison to some of the other solution types. And just as a quick note, I'll review these briefly at the end of the module. Well, first of all, as I mentioned in Module 1, I'm not going to be covering the photon map solution because, as far as I'm concerned, it became outdated the day that the light cache was developed. Now, the photon map is still an important feature for caustics, but with that exception, I wouldn't recommend its use over the light cache because the light cache provides a much faster and more accurate approximation. And this is really what it all boils down to, speed versus quality. And to achieve the same level of quality with other types, the settings have to be adjusted so high that their rendering times will almost always exceed that of the light cache. But why is the light cache so much faster? Well, the reason could be laid out in front of you in mathematical terms, but in a nutshell, light cache is able to compute a very large number of light bounces very quickly. As a side effect to this benefit, it's not as accurate a solution as the irradiance map, or as we'll discuss later in this module, the QMC, the quasi-Monte Carlo solution. And because it's not as accurate as these two methods, I wouldn't recommend using it as the primary bounce unless you're performing progressive path tracing, which is a great technique in which light cache is utilized for both primary and secondary bounces. This technique will be covered much later in Module 7, but for right now I'm limiting my use of the light cache to secondary bounces. Now, because the light cache is so good at calculating a large number of light bounces, it's very effective for interiors, where light tends to be trapped more and bounce around more surfaces than it does in exteriors. Additionally, the light cache effectively spreads out the light very well, making it even more effective for interiors. And smooth lighting is extremely important for nice interior images. I don't mean to take away anything from using light cache for exteriors, because personally I still use it more than any other type for both interiors and exteriors. I just wanted to make mention, and I'll hit on this again when I talk about the QMC solution later in the module, I just wanted to make mention that a large number of secondary light bounces just isn't as important for exteriors as it is for interiors. In fact, many users prefer the light cache exclusively for interiors while using the QMC exclusively for exteriors. When we get into the QMC, you'll see why, but for now, enough background talk about the light cache. Let's get into some real scenes. And if you want to follow along with this demonstration, open up the file called corridor.max. All right, in this scene I have just a few objects, a single object representing a long corridor, and 3 spheres placed along the length of the corridor. The only source of illumination is environment light, which appropriately enough is what we're going to be discussing at the end of this module. I'm going to render the scene as is, and notice also that I have the show calc phase option enabled, which allows me to see the light cache as it's being created. And when I render, you'll see a multitude of dots appear in the render window, and these are the samples being taken. Just like all rendering solutions, samples are the main ingredient in computing GI. Well, if you haven't already realized it, you may be surprised to hear that the secondary bounces were calculated before the primary bounces. I'm going to show this again by rendering the scene again. And there's the light cache, followed by the irradiance map. And why would VRay be doing this? Why would it be calculating the light cache first, the secondary bounces first? Well, like I said, the light cache is not as accurate as the irradiance map. So instead of calculating GI in a very detailed manner with the irradiance map and then calculating GI in a very rough manner with the light cache, VRay instead starts with the light cache to roughly approximate GI and then uses that information to more accurately and more quickly calculate a more detailed irradiance map. It just wouldn't make sense to do it any other way. Okay, so having said that, the samples that the light cache takes is controlled by the subdivisions value here within the light cache rollout. The number of samples taken is actually the square of this value. And to see this, I'm going to switch the primary bounce engine to light cache and enable the Don't Render Final Image option, and this will allow me to see the light cache samples instead of erasing them with the irradiance map or the final image. Now there's a setting in the light cache rollout called number of passes, and what this feature does is it allows you to take advantage of calculating a light cache with multiple threads or multiple computers by each thread or computer calculating part of the total solution. This is a great option for network rendering, especially when animations are being rendered. When the final light cache is shared among those threads or computers, it will lead to less variance in the GI from one frame to another, such as flickering, which is a very common problem in GI solutions. Now, for the purposes of this demonstration, I need to change this value to 1 simply to prevent a blending of samples from the multiple threads I'm using within my computer. Also, for this demonstration, I need to make my sample size something really high, like 1, so that it doesn't affect the number of samples taken. And you'll know in a moment why I say this. Finally, I'm going to set my subdivision value to 1 and render. And when I do, you'll see one lone dot appear in the render window, and this represents the 1 sample taken. If I increase this value to 2, you can count 4 samples. With a value of 3, you can count 9 samples, and 4 gives me 16 samples, and so on. So what should you use for the subdivision value? Well, like most areas of VRay that control GI quality, I recommend 2 ranges for subdivision values, 1 for test renders and 1 for production. For test renders, I would recommend values around 100 for large scenes and 250 for small scenes. As a general rule, for production renders, I simply multiply these values tenfold. So for production renders, I recommend starting with 1000 for large scenes and 2500 for small scenes. Values above 2500 should really be avoided because of the smaller and often negligible benefit that comes at a greater cost of rendering time. Likewise, values below 100 can provide really poor results and will almost never save a significant amount of time. That's just a quick demonstration of the subdivision setting. Now, I'm going to leave the passes at 1, but realistically, there's no real reason to change this default value. Technically, having 1 pass taken by 1 computer or thread means a more consistent light cache, and this is fine if you have a computer with only 1 thread, but the vast majority of users are using much more powerful computers like a dual core or a simple hyper-threaded Intel computer. If this is the case, you'd be shooting yourself in the foot to use lower settings. You can use higher settings, or you could increase this value to take advantage of the number of threads that you have available, but at some point you need to hold this value to ensure consistency in the light cache. Okay, now let's look at the relationship between subdivisions and sample size and how they interconnected. To make this as clear as possible, I'm going to make this connection visually and then explain what you're seeing. I'm going to switch the subdivisions value to 20, which means I'll have 400 samples to work with. I'm also going to switch this filter option here from nearest to none, and this is very important, but I want to wait until we're a little further along with the discussion of light cache, because talking about it right now might only confuse. And finally, I need to disable the don't render final image option. And when I render the image, I'm thrown back to the days of CGI graphics and 16-color computer displays. But what this cell-like image is really showing is 400 individually colored sample areas. I call them cells. They are individually colored according to the color detected by the sample, which was taken at the center of the cell-like area. Now, I'm going to re-enable the don't render final image option so that you can see the actual sample dots. When I superimpose these dots onto the final rendered image, you can see that the samples lie in the center of the cells. Now, I want to point out a really important concept about sample size and how it's interconnected with the subdivision setting. This can be kind of confusing, so I'll try to explain it as simply as I can. The sample size specifies the maximum allowable size of a sample if, and only if, there are enough samples to allow for the size specified with this setting. In other words, if I set the subdivision value too low and there just aren't enough samples being taken, it doesn't matter how small I make the sample size because all the samples have to be spread out to cover the screen. Okay, hopefully that wasn't too confusing. In the light cache rollout, there's another setting that determines final sample size throughout a scene. When the scale setting is set to screen, the sample size value is a fraction of the screen size. So when set to the default value of 0.02, the sample size value wants to limit each sample to be no larger than 2% of the screen size. This doesn't mean that the sample size will necessarily be 2% or smaller, because if there aren't enough samples to divide the image up into, then the actual sample size could be much larger. If you look closer at this image, you'll see that in fact these samples are much larger than 2% that I've indicated or dictated. And the reason why is because I haven't allowed VRay to take enough samples. Well, now I am going to allow enough samples to be taken. I'm going to use 200 subdivisions, and when I render, you can see that the samples reduce to their specified size of 2% of the screen size. If I increase the subdivisions value now and re-render, you'll actually see no difference in the size that make up the samples. Okay, now let's go on to the opposite direction and make the sample size be really large. When I use a value of 0.1, I'm telling VRay to make my samples no larger than 10% of the screen size. And when I render, you can kind of make out that the samples are approximately 10%, but because we took so many excessive samples, 40,000 to be precise, the cells aren't still defined by the same size, but their colors have been adjusted to reflect the additional information that VRay learned by taking the extra samples. This is really evident if I reduce the subdivisions back down to 20. When I render again, you can clearly see that the cells are much more differentiated, though no different in size or shape. Now let's look closer at what the scale setting means, and this is really important. If you look at the last rendered image, you'll see that all the samples are the same size relative to the camera's view. But look closely and you'll realize that a sample in the foreground represents a much larger area than the same sample size on the back wall of the corridor. And this means that the samples are less accurate when they are taken farther away from the camera. Although this isn't a problem from the current perspective, if you were to move down the hall and render this image again with this saved light cache, your image will likely not have as much quality. And let's see this. I'll change the subdivisions value to 100 and the sample size to 0.02. When I render the image, you can see that the cells on the back wall appear to be the same size as the cells in the foreground. Now there's some distortion because of the varying angles we're viewing some of these surfaces at, but all the cells are close to the same size, and you can see this most clearly by comparing the cells in the front of the wall to the cells in the back of the wall. In fact, I'm going to take a quick second to create another object here. I'm going to create a box, and I'm going to move it into just such a position that you can see a surface on the front, similar to what you would see on the back wall. And when I render this, it's pretty evident that the cells in the box are the same as the cells on the back wall. Finally, if I change the scale to world and set my sample size at 1 foot, when I render you can see that the samples are the same size everywhere in the scene, and therefore samples in the foreground take up more screen space than samples in the background. Notice something else interesting here as well. See how the shading of the cells changes from the front of the scene to the back? Why would this be? Well, I alluded to the reason a moment ago when I said that with excessive samples taken, more information can be used to define the color of the samples. So again, these cells in the foreground are the same size as those in the background, but the cells in the foreground actually had far more samples taken in their area and more information therefore to correctly shade their sample cells. But why isn't the light cache smoothing or blending these sample areas together so that they don't look so cell-like? Well, if you recall from Module 1, I created a circle and smoothed the curves of the circle by adding interpolation steps. Essentially, we have to do the same thing here. A moment ago, I mentioned that I needed to place the interpolation sample setting to none, and I did this to show the sample areas in their cell-like form. But now I want to bring the interpolation samples back so that they are smoothed out to a more pleasing appearance. So I set the interpolation samples back to nearest, which simply tells VRay to determine any given point by looking at the nearest X number of samples to that given point. If I set this value to 1 and render, you'll see that nothing has changed. And the reason why is that at any given point within the shaded cell, VRay is looking for the closest sample lying next to it, which of course is the sample that was used to color the entire cell. But if I increase this value to 2, VRay is going to look for additional nearby samples to help determine the final color of the given point. If I put this value back to the default value of 10, the result is a fairly smooth blend of sample areas. Now the final thing I want to do here with the light cache is restore this image back to a higher quality. So the first thing I'm tempted to do is try raising the subdivision value to something such as 500. When I render with a subdivision value of 500, it becomes obvious that this value alone is not going to restore our image. The biggest problem is right now we're wasting precious resources on samples in the background. And this is solely because we still have the scale set to world. Remember, for stills, there's absolutely no reason to use world. The world setting is only a worthwhile option for animations. And we'll discuss this further in Module 4 when we talk about animations. So I'll switch to screen and set my sample size back to the default value of 0.02, which is a good default value. And I'll render, and after a moment I'll see that something still is not right with my image. Earlier I stated that the light cache is not meant for detailed GI, and now we can see that this is really the case. Only way to get a really nice high quality image using a light cache for primary bounce is to use extremely high quality settings, which will simply result in much longer render times than you would get if you were just using the irradiance map or QMC instead. So that's the light cache in a nutshell, and hopefully you'll better understand what's going on behind the scenes when you use this GI solution, and hopefully you'll achieve much better results in much less time. Okay, now it's time to switch gears and look at the final render solution that we're going to be discussing in these modules, and that would be the QMC GI solution. Now the QMC solution is neither my favorite primary or secondary bounce solution, but I do use it on occasion for very specific things, which we'll discuss, and it is a completely sound choice for anyone deciding to use it. Everyone has their own methods of implementing GI, and this is certainly a favorite among many VRay users. Okay, let's look at what this solution is all about. The term Monte Carlo is used in mathematics to describe a method of solving complex mathematical problems, and this is done through the use of algorithms just like all the other GI solutions. The designation of Monte Carlo was actually first made in the 1930s, and it's a reference to the casinos in the city of Monte Carlo, Monaco, and it was chosen by a group of mathematicians that were relating the random and repetitive nature of the casinos to the similar nature of the algorithms which they created. The term quasi can be defined as having a likeness to something or similar to something. And therefore, by definition, the quasi-Monte Carlo method is similar to the Monte Carlo method with one important exception. Instead of using random sequences, the quasi-Monte Carlo method uses sequences that are uniformly distributed. VRay uses this same QMC approach to calculating global illumination. Another term in mathematics is brute force. This simply means to solve an equation by trying all possible solutions. As an example, applied to the field of cryptography, which is code breaking, it simply means to break a code by testing every possible solution. The QMC method is known as a brute force method because potentially it's capable of computing GI everywhere in a scene. This method is not adaptive like the irradiance map and the light cache because samples are taken in uniformly distributed areas regardless of the information derived from other previous samples. Although the QMC method is theoretically capable of calculating a perfect solution, this is really never a feasible or practical way of thinking. Like other rendering solutions, the QMC method is simply another way of approximating GI to a quote-unquote acceptable degree of accuracy. QMC is a great option for calculating GI in a scene for certain situations, but to better understand what those situations might be, you need to know what the advantages and disadvantages are of using the QMC method. When I talk about the QMC method, I like to point out that there's really 4 primary advantages for using the QMC method over other GI solutions. The greatest advantage of the QMC method is the ability to produce very accurate GI. The only competition that QMC has in this regard is the irradiance map, which, because of its adaptive nature, leads many to choose the irradiance map as their first choice for primary bounce. Remember that the primary bounce requires a high level of accuracy. Because the QMC method is referred to as an exact method, it should be no surprise that there are few controls used to dictate the quality of the image. And this is the second advantage. A third advantage is that because QMC doesn't store sample information for later use, it requires far less memory to use than adaptive methods. The fourth and final big advantage of the QMC method is that when rendering scenes with moving objects, besides the camera, which is not something that is actually rendered, it's the only alternative to rendering a scene in multiple passes and compositing the separate passes later. With adaptive solutions, you cannot render moving objects without doing so in multiple passes. This will be discussed in depth during Module 4 animation. Now, there's really only one main disadvantage of the QMC method for calculating GI, and unfortunately it's a big disadvantage, and that would simply be the time that it takes to create quality images. This one disadvantage makes this solution unacceptable for many users in many situations. To better determine when it might be appropriate to use this rendering solution, let's look at an example scene and compare the results of using the QMC solution with other solution types. If you want to follow along in the max scene, open up the file called gitest1.max. In this scene, which we've looked at before, we only have a few simple primitives, but when testing render solutions and their various parameters, it's important not to spend a lot of time conducting tests on complex scenes. As simple as the scene is, we're still going to conduct a render region of a small portion of the scene because some of the configurations that we'll be looking at will still take a good deal of time. So let's look at what GI settings we have right now. And if I open up the GI rollout, you can see that I'm using an irradiance map for the primary bounce and a light cache for the secondary bounce. In the irradiance map rollout, I'm using a low preset with a subdivision value of 20, and for the light cache, I'm using a subdivision value of 250. And all other irradiance map and QMC settings are set to their default values. I'll render the scene as is, and this is what I get. Now let's change the secondary bounce type to QMC and render with the default QMC settings. This is what I get when I do. And notice the high level of noise throughout the image. Why is this? The QMC method is supposed to provide a more accurate solution. So why does this image appear to actually be less accurate? Well, in a sense, it's showing a more accurate GI solution just not necessarily a better image. As described in the first module, the primary bounce is where detail is required, and both images have an irradiance map used as the primary bounce. As you may have assumed, the noise in the second image is coming from the secondary bounce. Unlike the light cache, which interpolates samples and blurs the secondary bounce GI to a much greater degree, the QMC is a brute force method, so GI samples are calculated independently of each other, and therefore no interpolation and no blurring can occur, which is also why there's so few settings that we're going to be dealing with. The only way to remove the noise is to improve the quality settings of the QMC solution. But to improve the image to an acceptable level, the quality of the QMC must be improved so much that the rendering time would increase so dramatically. The QMC would therefore be a poor choice for the secondary bounce in many situations. For this reason, the light cache is usually preferred as the secondary bounce solution. Now let's look at the same scene while comparing the irradiance map to the QMC for the primary bounce. To do this effectively, we'll need to make the secondary bounce solution be the same in both scenarios, and as we just saw, the light cache really is the best option for doing this. In this next demonstration, I'm making light cache subdivisions at 250 and leaving all other settings at their default value, and I'm just doing this so the light cache renders pretty quickly, and it's still going to give me a decent solution. First, I'll render the scene with an irradiance map using the same settings used in the last demonstration, and this is what I get. Now I'm going to change the primary bounce to QMC, and with the default settings, this is what I get. Again, it would appear from all the noise that the GI in this image is much less accurate than the GI in the previous image created with an irradiance map. But as before, this is not necessarily the case. The image contains noise because the GI samples are calculated independently from each other and not blurred together. We simply haven't given the QMC algorithm a chance to do what it's capable of, i.e. bring out detail and be more accurate. So how do we do this? Well, the answer lies in two different rollouts. The Quasi-Monte Carlo GI rollout shown here directly controls one aspect of the solution quality. Here we have another subdivision setting which works in a similar fashion as other subdivision settings discussed thus far. Notice that we have another setting, secondary bounces, but this setting is ghosted out. This is because the setting controls the number of times light processed by the secondary bounce solution is allowed to bounce from one surface to another. Since the QMC method is not the secondary bounce solution, this setting cannot control the number of secondary bounces, therefore it's ghosted out. By increasing the subdivision value, we can dramatically improve the quality of the image. Increasing subdivisions increases the number of samples taken, thereby reducing the noise. At a value of 40, the image looks like this. And notice the noise is very small, but the rendering time increased from 1 minute 37 seconds to 3 minutes 6 seconds. The increase in quality comes at a hefty price when using a brute force method. But the Quasi-Monte Carlo GI rollout is not the only section in VRay that controls the quality of the GI solution. The QMC sampler shown here plays a critical role in specifying the GI solution quality. But the settings in this rollout do not only control the quality of the QMC GI, they also control, at least partially, the quality of all blurry values in G-Ray. A blurry value in VRay is any value that provides a blurry look, such as motion blur, depth of field, area lights, blurry reflections, or in the case of our discussion here, QMC GI. In just a moment, we'll look at some of these other blurry values and see how these settings control them. For now, let's continue the discussion about QMC GI. In VRay, there's a term called importance sampling that describes the technique of controlling the number of samples taken for a blurry value based on the importance of the value. By setting this parameter to its lowest possible value of 0.0, you're telling VRay that you don't want to conduct importance sampling and therefore don't want VRay to base the number of samples taken for a blurry value on how important the value is. By setting this parameter to its highest possible value of 1.0, you are telling VRay that you do want to abbreviate the QMC GI algorithm for each blurry value based on their importance. And why would you want to do this? Well, just like any other area of VRay, we want to save time. So before we go any further, let's render a few examples with these settings in action. I'm going to place the QMC GI subdivision value back to its default value of 8 and leave all the other QMC sampler values to their default value. And when rendered, this is the image I get. Notice the noise is returned because of the low subdivision settings that we're using. Now I'm going to change the adaptive amount value to 0.0 and render the scene again. This is what I get. Notice the increase in rendering time, yet no improvement in GI. And the increased render time came because we told VRay not to adapt to the situation and therefore not abbreviate the rendering algorithm. But since we're only specifying 8 subdivisions, not abbreviating the rendering solution does not mean that we're going to have a nice GI solution. With 8 subdivisions, we're simply not giving VRay enough information to work with. Now, another critically important setting in all of this, and one that confuses a lot of people, is the noise threshold value. When some users see this setting, they naturally tend to think that it will automatically remove noise in their scene. This is not necessarily the case. It can, but only when used correctly in conjunction with the blurry value in question and the adaptive amount value. In this case, the blurry value in question is the QMC GI subdivision value. So what do you think would happen if I increase the noise threshold value to its maximum value of 1.0? If you think it will have any effect on the noise in this scene, you'd be wrong. So let's see this. And this is what I get. As you can see, there's no change in the QMC GI quality and no change in the rendering time. So why is this? Well, it's because the noise threshold is only a control for the importance sampling, i.e. the adaptive amount value. If you don't conduct any importance sampling, i.e. if the adaptive amount is set to 0, then you cannot specify how much noise you want the importance sampling to be governed by. Now I'm going to tell VRay to become fully adaptive and spend some time trying to figure out how to shorten the algorithm according to my noise threshold. As you can see, with a noise threshold of 1.0, VRay actually spends more time producing a lower quality image. It's difficult to quantify the number of samples taken when you don't actually have the ability to see these samples like you do with the irradiance map and the light cache. My only conclusion from this result of increasing render time is VRay is trying to internally resolve some unreasonable requests between the importance sampling and the noise that the sampling is controlled by. And now I'll reduce the noise threshold to the default value of 0.01, and as you can see, the noise in the image is significantly reduced, and it comes at a dramatic reduction in rendering time. However, the noise is still not at an acceptable level. So I will reduce the noise threshold to its lowest possible value of 0.0 and watch what happens. Absolutely nothing. There is no change whatsoever to the rendered image. And why would this be? Well, it's because we're simply not giving VRay enough samples to work with. And why don't we have enough samples? Because we have the subdivision value set too low. The only thing we can do to decrease the noise at this point is to increase this value. Let's try a value of 20, and when I render, this is what I get. And finally, I want to see if I can improve the quality even more by not conducting any importance sampling. So I reduce the adaptive amount to 0.0, and this is what I get. A slightly improved image at a cost of 50% more rendering time. To summarize all of this, the noise threshold value only plays a role when importance sampling is conducted, and importance sampling only plays a role when a blurry value has enough subdivisions, thereby generating enough samples. But remember that the values in the QMC sampler rollout affect all blurry values, not just the QMC GI. For this reason, I highly recommend making sure first that each blurry value is set properly. Then and only then can you experiment with various noise values, leaving the adaptive amount set to 1.0. The smaller your adaptive amount, the less effect your noise value will have. For most situations, I have found that increasing the adaptive amount to its highest value gives you the best speed versus quality. There are two other settings worth mentioning in the QMC sampler rollout: the global subdivisions multiplier and the min subdivisions value. By doubling the global subdivisions value, you're telling VRay to double every subdivision value in the program, with the exception of the subdivision values for light cache, caustics, photon map, and image sampling. Some use this to quickly increase the quality in their scene, but I really don't recommend doing so. It would be like putting a cast on a sprained but not broken leg. It will definitely improve the quality of a problem setting that you may have in your scene, but it's also likely to improve settings that really don't need improvement, and thus lead to dramatic increases in rendering time, especially if you're not careful. The same applies to the minimum subdivisions value, the minimum samples value. It can be hard to specify a minimum samples value when you don't even know what the true number of samples you're working with are, and even if you did, you might be applying a much higher quality setting to an area you're seeing that doesn't simply need the higher setting. Before we leave a discussion on QMC GI, I want to talk about real quickly the second of only two settings within the QMC GI rollout, the secondary bounces setting. This option is only available when the QMC solution is selected as a secondary bounce type. When it is, you can specify exactly how many times light bounces around outside your view. This can be helpful for reducing rendering times when using QMC as a secondary bounce. As a matter of personal preference, I prefer to always use the light cache for secondary bounces, but many users like the QMC for exteriors, and the ability to limit the number of secondary bounces is a big reason why. With the light cache, you can essentially achieve a very large number of secondary bounces with a relatively small amount of rendering time relative to other GI solution types. For interiors, a great number of bounces is far more important than it is for exteriors. Color mapping is a term used to describe the way VRay changes the final color of your screen's pixels to adapt to the limitations of the typical computer display. It works much like the exposure controls on a real camera or even within Macs. It can also be compared to the way the human eye changes to allow more or less light to enter the retina. Color mapping is a requirement for any rendered image, and as you'll see, it is far less difficult to understand than the topics we've discussed up to this point. As mentioned, color mapping is a lot like exposure control, and while you could use exposure control in the environment effects dialog box, I wouldn't recommend doing so because color mapping in VRay provides much more power and versatility than the exposure controls native to Macs, and using both color mapping and exposure control would be like using exposure control twice. The results are difficult to predict and usually not very good. Well, all of the color mapping controls are found here in the color mapping rollout, and in the drop-down list we have 7 different options to choose. By default, linear color mapping is employed, and all this option does is multiply the final intensity of all pixels within the 0 to 255 range, and it does so in an equal amount. For any color, an intensity of 0 results in a pure black pixel, and for any color, an intensity of 255 results in a pure white pixel. So all the pixels that want to be displayed in this range are adjusted to the same degree, either up or down in intensity. But some pixels actually want to be displayed above this 255 level. If, for example, you look at the sun with the naked eye, you naturally want to squint or shut your eyes to keep them from being damaged. Yet, if you just take a picture of a midday sun and look at it with the naked eye, all you see is the color white. Well, when you look at the sun with the naked eye, you see pure white, which corresponds to a color of 255, but the sun shines with luminosity or radiation, which is actually what burns your eyes. The color of the sun is captured in a photograph as pure white and nothing more because the illumination is clipped at this 255 value. The same thing happens automatically with color mapping. Illumination in an image that wants to be higher than this value of 255, such as a direct view of a VRay sun, is clipped at this value. Now, although there are 7 different options for color mapping, I recommend using one of 4 different options: linear, exponential, HSV exponential, or Reinhardt. And let's look at these other three briefly that we haven't talked about. The exponential option saturates a pixel, i.e. adds color to a pixel based on its intensity. And what this means is that pixels that are really intense or bright white will be given more color, thereby replacing the white with color. And pixels that are less intense will be given less color. So the end result is that brighter areas in the scene will not appear to be so bright, and dark areas will not appear to be so dark. So let's see this. In this scene, which I'm rendering with linear color mapping, I have direct light striking parts of the scene with a light that has a very high intensity. Notice these burned out high intensity areas here. I'm going to load this image into the RAM player and render the scene again with exponential color mapping. And with exponential, I can see that the pixels that were previously burned out are now replaced with color. The brighter the pixels, the more color they received. Conversely, the pixels that were previously not so bright didn't receive as much color. And therefore, all the pixels are closer together in both color and intensity. This, in effect, is exposure control, and this is a great tool to control overly bright areas and make dark areas of your scene not appear to be so dark. Now let's look at another great option for color mapping, HSV exponential. HSV stands for hue, saturation, and value. What this option does is it preserves the hue and saturation, i.e. doesn't change it, but rather changes the value of a pixel color based on its intensity. And let's see exactly what I mean by this. So I'll switch to HSV and render the scene again. Now I'll load this image into RAM player, and so we have HSV on the left and exponential on the right. I want to focus on this particular highlight right here, so I'll move the window divider on this highlight. Now I'll open the color selector and bring up the actual color that is applied to the torus. So what did HSV do? Well, look closely at the highlight and you'll see that instead of allowing this area to be washed out with white, it instead preserved the hue shown here on the color spectrum, and it also preserved the saturation shown here. So instead of changing the hue and the saturation, it instead only changed the value of the color as I'm doing here. The more intense the pixel, the more value it added. The less intense, the less value it added. And that's all that's going on here. It's really that simple. The end result of this type of color mapping is a more vibrant display of colors and less intensely illuminated areas. Now, you may want bright, washed out, or overly lit areas of your image, in which case this really wouldn't be a good choice. But if these qualities aren't needed, then HSV might be a mapping type that you might want to try. The final color mapping I want to explore is Reinhardt. This is my personal favorite, and all it does is provide a mixture of linear and exponential. The mixture of these two color mapping types is controlled by the burn value shown here. When burn is set to 1.0, the result is purely linear color mapping, and when burn is set to 0, the result is purely exponential. And as a matter of preference, I always start my scenes with Reinhardt using a burn value of 0.5. When I do, I'm telling VRay I want a 50-50 blend of linear and exponential. And I've just found that this is a great place to start test renderings and a great place to start my color mapping. Just like so many other areas of VRay, you really need to test different color mapping types in different settings within these various types. So in the case of my preferred choice, Reinhardt, if I render a scene and determine that there's just too many areas of overly bright highlights, all I need to do is reduce my burn value and bring it closer to exponential color mapping. There's one more feature in color mapping that I want to point out, and this one can really help improve the look of your scenes by fixing a really common problem in visualizations. With the first 4 color mapping types available in the drop-down menu, you're given the ability to increase or decrease the illumination of dark areas of your image separately from bright areas of your image. Raising the bright multiplier increases illumination in already bright areas of your scene, and decreasing the bright multiplier decreases the illumination. The dark multiplier works the same way, therefore raising the dark multiplier increases illumination in already dark areas of your scene, and decreasing the dark multiplier decreases the illumination. And to see this, I'm going to open a scene similar to the one we've already worked in, but this one has a ceiling overhead except for a small opening on two sides of the square room that we're in. If I render this as is with linear color mapping, I can see that I have a decent looking image, but what if these dark areas are too dark? What can I do? Well, as I said, Reinhardt is my favorite color mapping type, but when I need this kind of control, I need to switch to another mapping type such as linear or exponential. So to make these dark areas a little brighter, all I have to do is increase the dark multiplier. And when I render, I can see in fact that the dark areas got brighter. I can go in the opposite direction and decrease take light away from the already dark areas by decreasing the dark multiplier. And I can do the same with the bright multiplier. Decreasing the bright multiplier decreases the illumination in all the bright areas of my scene. And notice also the background decreased in illumination. I can disable this effect, or this side effect if you will, by disabling the affect background option to prevent this from happening. The final area I want to cover in Module 2 is environment lighting. Now, a discussion of this particular area of VRay can lead to lengthy coverage over a wide range of similar topics, such as HDRI lighting, which stands for High Dynamic Range Images, more simply image-based lighting. This particular topic and several other topics could be included in the discussion right now, but I'm not going to do so soon in these modules. My intent here is to simply introduce the concepts that we can build on in other modules, and so I just want to make sure you understand all the major components, i.e. the critical settings that go into illuminating scenes that we'll be working in, and environment lighting, as I'm going to explain it now, is one of those. Again, these first two modules are just the critical settings, and I want to keep as many variables out of the equation as I can. So environment lighting is simply illumination of a scene with skylight. But the skylight that I'm talking about can be created in a number of different ways. It can be image-based, which means using HDRI images, as I just mentioned, to store or project luminosity into a scene. It can be a VRay dome light, which we'll talk about in the module on lighting. It can be a VRay sky map, also discussed in the module on lighting. It can be a IES sun, or it can be controlled right here through the environment rollout. All I'm going to talk about right now is the illumination of a scene through the environment rollout. So using the same scene I already have open, if I want to increase the apparent illumination due to the effect of skylight, all I need to do is increase this multiplier. When I render the scene again, I can clearly see that my entire scene is more illuminated. And a nice effect for interiors is to use a high multiplier value to get this nice washed out look where the light enters the room. The smaller the opening the light has to come in, the greater you can raise the multiplier value. Now, the strength of the environment light is controlled not only by the multiplier value, but also by the color swatch shown here. With a pure black color, there will be no skylight, and with a pure white color, there will be full skylight, or at least as much as the multiplier value will allow. The color not only controls the strength of the skylight, it also controls the color. So if I wanted to simulate the kind of skylight you would see during a sunset, all I need to do is select the appropriate color, dial up or down my multiplier value, and I get that kind of skylight. Now, I forgot to mention that this feature is not even on by default, and unless you enable the GI skylight override inside the environment rollout, VRay is going to use whatever color you've selected in the environment and effects dialog box to create skylight. So if you don't want skylight at all, simply make sure the color is black here. Now, one final note about the environment rollout. The top part of the rollout controls skylight, but You're also given the ability to control a different look to skylight in reflections and in refractions. And as a quick example, if I change the reflection environment light color override, I will see that color in all the reflected surfaces that show the 3ds Max background in all the reflections. Okay, now I just want to summarize what we covered in this module, Critical VRay Settings Part 2. There were 4 major concepts: light cache, quasi-Monte Carlo GI, color mapping, and environment lighting. With the light cache, we saw that it provides a great mixture of speed and quality, and the primary reason it can do this is it can compute a very large number of bounces very quickly, and that helps to add to the smoothing look to the GI, which it provides much better than the irradiance map and quasi-Monte Carlo GI. Now, the subdivisions values is what controls the number of samples. Number of samples is actually the square of that value. And the sample size will determine the max size of the sample areas if and only if there are enough samples. If there are not enough samples, then the sample size area will be much larger. The screen option is a great option for stills, and the world option should really only be used for animations in which you move in and around your scene. And the more you move through your scene, front to back, the more that really applies than just moving side to side or left to right. If you are having problems with blotches and you want to smooth out those blotches, smooth out the GI, you can always try to increase the interpolation samples to do so. And the light cache is really best utilized for secondary bounces because unlike the quasi-Monte Carlo GI and irradiance map, it was not made for details. And because it's a good secondary bounce and because it provides a good smooth look, it's a great option for interiors, which is what it's most widely used for, although many still use it for exteriors, myself included. Quasi-Monte Carlo GI is simply a brute force method, and as it states here, it is capable of calculating a quote-unquote perfect solution, although that's really not possible. This is just in theory. And it's guided by primarily the subdivision value in the QMC GI rollout and the values in the QMC sampler rollout. Now, the QMC sampler rollout does not just control quasi-Monte Carlo GI, it controls all settings, all values in VRay that are blurry values. Blurry values are anything like depth of field, motion blur, etc. Now, the noise threshold within the QMC sampler rollout is completely useless if there are not enough samples for each particular blurry value that the noise threshold has an impact on. And it also does not affect the quasi-Monte Carlo GI if there is no important sampling, and important sampling is controlled by the adaptive amount. So if the adaptive amount is 0 and there is no important sampling, the noise threshold will do nothing for you. And be careful of using minimum samples and the global subdivision multiplier, because changing these from the default value of 1 can really slow down your renderings, can really have a global impact to all the subdivision values in VRay. Quasi-Monte Carlo GI is really best utilized for primary bounces because of the detail it can provide, and people do use it for secondary bounces simply because they can control the exact number of bounces, and because of that it's most commonly used for exteriors when it is used as secondary bounce, where people can control the number of bounces and not let it go to a ridiculous amount. Color mapping is simply the changing of colors of pixels in the final image based on the display limitations that computers have. And not just computers, but any display, TVs also. Every image has it. You can't do without it. And there's 7 different types. There are 4 that I recommend using: linear, exponential, HSV, exponential, and Reinhardt. Reinhardt being my personal favorite. You never really want to use exposure control when you're using color mapping. It usually leads to bad results and unpredictable results. And one of the greatest things about some of the different options like linear and exponential is you can control the illumination in bright areas separately from dark areas. That is a tremendous benefit to some of these different options. Reinhardt, again, my personal favorite. It provides a mixture of linear and exponential. Using a burn value of 0.5 will give you a 50-50 mix. If you want to make it a little brighter, a little more towards the linear side, increase this value. If you want to reduce it, you can take it to the exponential side. And something I didn't talk about, I just realized you can use the gamma value and actually decrease the gamma value to help create moods that otherwise would be a little more difficult to set up, and such a type of scene would be a night scene. It provides great options for doing that. And last, environment lighting is nothing more than the illumination of a scene through skylight. And there are numerous ways to do this. It can be done through images such as HDRIs, high dynamic range images. It can be done through the use of a VRay light, a dome light. It can be done through a VRay sky map. There are numerous ways to do it, including what we saw just a few minutes ago, using the environment rollout. And by default, the environment color swatch is not activated, and if you do, you can override the color that is in the environment effects dialog box. The color swatch within the environment rollout provides a great way to add color to the skylight and give your scenes a very specific look. And that concludes Critical Settings Part 2.